Hello everyone, in this particular session we are going to calculate what is the time delay that is introduced by the timer when a particular value is loaded in a timer register, as well as if you want to have a particular delay in a timer, so what is the custom value that is to be loaded in the timer. We are going to work out on specific problems in this session, as well as we are going to use a Keil and run that problem in the software, and then we are going to validate the time delay using logic analyzer provided by the Keil and verify it with the time delay that we have set. Okay, so let us start with the time delay calculation in a timer. Now let us assume that the clock frequency of the timer is 11.0592 megahertz. If this is the clock frequency, then the machine cycle frequency is clock frequency divided by 12, because 12 cycles of a clock make a machine cycle. So the clock frequency divided by 12 gives us 921.6 kilohertz. Now, given this data, the time taken by each machine cycle is 1.085 microseconds. Now this particular value 1.085 microsecond is very important, because this is the time taken by each tick of the timer. I repeat it, each tick of a timer takes 1.085 microseconds when the clock frequency is 11.0592 megahertz. Now having said this, let us calculate what is the maximum permissible delay that is introduced by the timer in each of the mode. Okay, so let us consider mode 0. In mode 0, the maximum possible value that the timer can be set is FF1F. So for convenience sake, we'll take it as 1F FF. So if that is the value that is set, then the timer will increment from 0000 to FF1F and back to 0000. So FF1F is in hexadecimal is equivalent to 65311, or for convenience sake we'll say 1FFF. 1FFF is equivalent to 8191 in decimal. So timer in mode 0 will make a maximum of 8192 increments. That means it will go from 0000 to FF1F and roll back to 0000. So that is equivalent to 8192 counts. So 8192 counts into 1.085 microseconds gives us, okay, I'm sorry, I have to set the calculator in the decimal mode. So 8192 counts into 1.085 microseconds gives us 8.88 milliseconds. So the maximum possible delay that can be attained in timer in mode 0 is 8.88 milliseconds. Okay, sorry. Now let us consider timer in mode 1. When the timer is in mode 1, the maximum possible value that can be attained in the timer register is FFFF. So that is equivalent to 65535. So the timer will start from 0000 and it will go to FFFF and then roll back to 0000. So that means to say it is taking 65,536 increments, and each increments take 1.085. I'm sorry, 65,536 counts, and each of the counts take 1.085 microseconds. So the total possible delay that can be achievable in timer being set in mode 1 is 71.1 millisecond. Okay. Now what about timer in mode 2? Now when the timer is in mode 2, the maximum possible value that can be achievable is FF, that is 255. So the timer starts from 00 in the worst case condition and goes to FF and rolls back to 00. So there are 256 increments. When there are 256 increments, so each of the increment takes 1.085 microseconds. So the delay possible delay that can be provided by timer in mode 2 is 277 microseconds. Okay. Now having said this, let us go and work out on few problems. Here are three problems. The first problem is to generate a square wave using timer in mode 0 in pin P1.5 with a duty cycle of 50%, and it states that use maximum possible delay, and the clock frequency is 11.0592 megahertz. The second problem is to generate a square wave using timer in mode 1 in P1.5, and the third problem is to generate a square wave using timer in mode 2. Let us assume that we will use timer 0. Okay. So let us go to the Keil. Now I have a program here. T mod is set to 00. That means the timer is in mode 0. Now when you are set to generate a maximum possible delay, the maximum possible delay can be achieved when TH0 and TL0 are 0000. The reason being, if it is set to 0000, then it has to increment all the way up to FF1F in T mod in the timer and roll back to 0000. I repeat it. When the TH0 and TL0 are set to 0000, then it has to increment all the way up to FF1F in T0 and roll back to 0000. So the maximum possible delay is achievable in a timer when both TH0 and TL0 are initialized to 0000. So once you have initialized TH0 and TL0, then you will run the timer, and since the objective is to generate a square wave in pin 1.5, so we will keep on complementing pin 1.5. That means if the initial value is 0, then it will be set to 1. Okay, and then it will wait for the timer to overflow. Once the timer overflows, and when the timer overflows, the program will come out of this particular loop, and then it will go back and reload the value of 00 to TH0 and 00 to TL0, and again the timer will run, and if the pin 1.5 is 1, then it will go back to 0. So pin 1.5 will alternate between 0 and 1, hence generating a square wave. Now let us compile this particular program. Okay, there are no errors. Okay, now I will go to the debug mode. Okay, so now what I will do is I will use a logic analyzer and see what is the output waveform generated. Now how do you use a logic analyzer? Go to the view menu and click go to the analysis window and click on logic analyzer. Okay, I repeat it. Go to the view menu, click on analysis window, and there you see a logic analyzer. So click on that. So you will see a new window called as logic analyzer, that is a view that is popped up. Okay, now before you use the logic analyzer, you have to set up the logic analyzer. Okay, the way you do this is, there is a button called as setup. If you can see here on the top left corner of the logic analyzer window. So you click on the setup, and you can see a dialog box that has popped up. Now in the dialog box that has popped up, there is a dotted rectangle icon on the right hand side which says insert, new insert. So your objective is to monitor P1.5 because P1.5 changes from 0 to 1 and 1 to 0. Okay, so you enter P1.5 in this particular box, okay, and you say okay. So basically what has happened is port 1 has been added to the logic analyzer. Okay, now so the P1 alternates between 0, that is the lower limit, and 1, that is the upper limit. So we will set the lower limit to 0 and we'll set the upper limit to 0, 2. Okay, so then we will close this particular dialog box. Okay, now so we will run this particular program. In order to run it, you see a run icon, just run this particular icon. Okay, now you can see that the output is displayed in the logic analyzer window. So we will stop the program. Okay, so as per our earlier session, when the timer is in mode 0, the maximum possible delay that can be achieved is approximately 8.88 milliseconds. Okay, so I am going to focus at the transition. So when I focus on the transition, you see that it's approximately, it's stating 8.99 milliseconds. Now I was expecting 8.88 milliseconds, but it shows 8.99 milliseconds. Now why is it so? Okay, so for that you need to understand this particular delay introduced by this particular program. Now here the timer is introducing a delay, but at the same time there are multiple commands in the program. If you see, the first command introduces a delay of 2 machine cycles, second command introduces a machine delay of 2 machine cycles, so on and so forth. So if you want an accurate calculation of the delay, then you should consider not only the delay introduced by the timer, you have to also consider the delay introduced by each of the respective instructions. So okay, let us check the second program to create a square wave using timer in mode 1 in pin 1.5 with a duty cycle of 50%. Use maximum possible delay and assume that the clock frequency is 11.0592 megahertz. Now let us go to the Keil session. So when the timer is in mode 1, the T mod should be set to 01, and to achieve a maximum possible delay, T0 should be set to 0000 because it should start from 0000 and reach till FFFF, since the timer is in 16-bit mode now, and then roll back to 0000. So we set TH0 to 00 and TL0 to 00 and then run the timer and keep on complementing P1.5 to generate a square wave. Now let me compile this program. Okay, there is no error, and let me put the session in the debug mode. Okay, as per my earlier calculation, when the timer is in mode 1, the maximum possible delay that can be achieved is approximately 71.1 milliseconds. So let me run this particular program. Okay, and let me zoom out. Okay, so I'll stop the program, zoom in. Okay, so as I said before, the maximum possible delay is 71.1 milliseconds. So I am focusing on the transition. If I focus on the transition, it says that the transition happens at a duration of 71.19 milliseconds. Okay, and the time period for the entire square wave form is approximately 0.1423 seconds, that is 71.1 milliseconds into 2, that is 0.142 seconds. Okay, so we'll go to the last program. Write a program to create a square wave using timer in mode 2 in P1.5 with a duty cycle of 50%. Use maximum possible delay assume clock frequency of 11.0592 megahertz. Now we'll go back to the Keil session and we'll stop the debug session. Okay, when the timer is in mode 2, we have to set the T mode to 02 and we have to assign the reload value to TH0. For maximum possible delay, the reload should be 00. That means the timer should start, TL0 should start from 00 to FF. Okay, once it rollovers, the TL0 will get loaded with whatever is present in TH0, that is 00. Okay, so let me compile this. Okay, and before proceeding further, let me go to my calculator and calculate what is the expected maximum delay. So in timer, for the timer in mode 2, the maximum possible delay happens when it rolls from FF to 00. So there are 256 counts and each of the counts gives me a delay of 1.085 microsecond. So the total delay that is provided by the timer is 278 microseconds or 0.278 milliseconds. Okay, so let me put the session in the debug mode. Okay, and let me run the timer. When I run the timer, and I'll stop it, and now zoom in. I'll zoom in. Okay, so I'm expecting 0.277 milliseconds. So if I focus on the transition, it says that the transition occurs at 0.297 milliseconds. I was expecting 0.277 milliseconds, but it is happening at 0.297 milliseconds. The reason for this is whenever the timer count becomes very less, so at that point what happens is the delay due to the instructions present in the program becomes significant. That means even though the timer is offering a delay, okay, each of the instructions in the program also offer some machine cycle delay. So when the timer count is less, the delay offered by each of the instructions becomes significant. So that is the reason why you see the deviation of the calculated versus the actual value. Okay, the next program is to demonstrate square wave generation at a frequency of 10 Hertz. So for what we have been focusing is we are setting the values of TL0 and TH0 to some minimum value, and then we are calculating the time period. Now we are doing the other way around. So given a time period, we have to find out what is the value that has to be loaded in TH0 and TL0. Now for a frequency of 10 Hertz that has to be generated in P1.5 with the clock frequency of 11.0592 and mode 1, the time period would be 100 milliseconds. Okay, so now if the time period has to be 100 milliseconds, so then P1.5 has to be high for 50 milliseconds and low for another 50 milliseconds. So the delay that has to be provided by the timer in mode 1 is 50 milliseconds. Okay, now for every tick of the timer, the delay offered is one machine cycle, that is 1.085 microsecond. So if we want to get a delay of 50 milliseconds, then we need to have a tick of 46,083 in the timer. Okay, that translates to B403. Let me repeat this again. Every tick of a timer takes 1.085 milliseconds, okay, microseconds, and if you want to get a delay of 50 milliseconds in a timer, then the timer has to tick for 50 milliseconds divided by 1.085. 0.85 microseconds. So that is 46,083. Now, can the timer tick for this interval, or can the timer increment by this amount? Yes, in timer 1 it can increment, because the maximum possible value that can be attained is 65,535. So with this particular value 46,083 is within that maximum possible value. So the timer can increment to this by this extent of 46,083. So if we want to increment the timer by this amount, we have to work backwards from FFFF and achieve a value of timer that has to be set. So if now when we convert this 46,083 decimal to hexadecimal, we get B403. Now we have to work backward to see what is the value of the timer to achieve a tick of, or the increment of B403. So that means the value of the timer that has to be set is FFFF minus B403 plus 1. Okay, so that yields a timer value of 4BFD. So 4B has to be loaded to TH0 and FD has to be loaded to TL0. Okay, so let us go back to the Keil, and I will set the timer in mode 1. Okay, and change the value of TH0 to 4B and value of TL0 to FD 0 FD. I'll put everything in the caps just for my convenience. So let me verify 4B FD. Okay, 4B FD. Okay, so 4B is loaded in TH0 and FD is loaded in TL0. So let me compile this project, and let me go to the debug session. Now let me run this program. Okay, and zoom out. Okay, so stop. Okay, so as per the question, so my frequency should be 10 Hertz, that is the time period should be 0.1 seconds. Let us see whether we have achieved it. I'll focus here at the transition. The transition happens at approximately 50.39 and the time period is approximately 1.1 seconds. So, okay, 0.1 second. So so the entire time period has taken 0.1 seconds. So the frequency of oscillation is 10 Hertz. Okay. In this example, we are going to generate a square wave and timer that is set in mode 1, and the frequency of the oscillation should be 0.1 Hertz. Now, if the frequency of oscillation should be 0.1 Hertz, then the time period of the square wave is 10 seconds. Now, if the time period is 10 seconds, so the P1.5 will be high for 5 seconds and will be low for another 5 seconds. So the timer has to generate a delay of 5 seconds. Now, in our previous session we have said that if the timer is in mode 1, the maximum possible delay that can be achievable in mode 1 is 71.1 milliseconds. So can we generate a delay of 5 seconds using timer in mode 1? Not exactly. So what we do is we split 5 second time interval into 100 intervals of 50 milliseconds each. Now 100 intervals of 50 milliseconds will be 100 into 50, that is 5 seconds. Now since the maximum delay that can be produced by a timer in mode 1 is 71.1 milliseconds. So naturally the timer can produce a delay of 50 milliseconds. So what we will do is we will calculate the value of timer that has to be set to provide a delay of 50 milliseconds first. Okay, so if the timer has to provide a delay of 50 milliseconds, so it has to increment 46,083 times, that is 50 milliseconds divided by 1.085 microseconds. That gives you value of 46,083 counts. Okay, now these are the number of counts, so we have to work backwards to see what should be the value of timer that has to be set to achieve a tick or increment of 46,083. So that is achieved by subtracting B403 from FFFF and adding 1. So the timer value that has to be set to achieve a delay of 50 milliseconds is 4BFT. So TH0 should be assigned 4B and TL0 has to be assigned FD, and this provides a delay of 50 milliseconds, and that has to be iterated 100 times to get a delay of 5 seconds. Now let us go to Keil. Now in Keil, timer is set in mode 1 and we complement P1.5 and we set R4 to 64 hexadecimal, which is nothing but 100 decimal. So then we set the value of TH0 to 4B and TL0 to FD, and we run the timer. So the loop generates a delay, this particular loop generates a delay of 50 milliseconds, and that is iterated 100 number of times. If you see here below, it says that decrement jump on no zero R4 loop. So this particular loop will be executed 100 times, and each time this loop provides a delay of 50 milliseconds. So the total delay provided by this is 5 seconds. Once the delay is for 5 seconds is generated, then it will go back and complement P1.5 and it will redo this logic again, okay, or re-execute this logic again. So let us compile this particular program and go to a debug mode, and then I will run this particular program and let us see the output of the logic analyzer. Okay, so let me zoom in. So I expect the transition to happen at approximately 5 seconds. Okay, so let us see whether the P1.5 will change from 0 to 1 at this duration. Yes, the P1.5 has changed from 0 to 1 at approximately 5 seconds, and subsequently at the 10th second it will go back from 1 to 0. So let us see that. Okay, so it has made a transition from 1 to 0. So the total time period is 10 seconds. So the frequency of oscillation is 0.1 hertz. Okay, so having said this about the timer, now we will talk about one specialized mode of a timer, and that is called as a counter mode. Now the counter mode is a mode when the timer derives a clock frequency from the external source. Now let us let us analyze the particular program of the counter. So when the counter is to be used, at that time we have to set C/T bar to 1. So for a timer 0, the C/T bar is bit number 2. Bit number 0, bit number 1 are the mode setting bits, and bit number 2 is C/T bar. Okay, so if the bit number 2 has to be set, I will use the binary notation. So it is T mod is 0 0 0 0 0 1 0 1. So the timer is in mode 1, but at the same time the timer is set to the counter mode. So in this counter mode, what I am doing is I am complementing P1.5 and I am running this timer, but the timer has to make a transition, or the timer will be incremented if and only if the T0 pin, that is port 3.4 P3.4 is clocked. Okay, so let us compile this particular program, and let me put this program in a debug mode, and let me execute this particular program, and let me go and fetch the value of the ports. Okay, let me see, monitor the port, and also I'll monitor the timer. Okay, now as I said, the timer is in counter mode. Okay, so now we will remove all the values, we will reset all the values of the pins in port 3. Now my interest is to run this timer in a counter mode. So this particular input has to be provided to pin 3.4. This is P 3.0, 3.1, 3.2, 3.3, 3.4. Now as and when I provide an input to P 3.4, observe the timer value. Okay, I will provide an input and I will reset the input, provide the input and reset the input. If you see, as and when I provide the input and reset the input, the value of TL0 is changing. So this means that when the clock is available to the pin 3.4, that is T0 pin, so the timer, if it is being run, the TL0 will keep on incrementing, and if the timer is in mode 1, so the combination of TL0 and TH0 will increment. That means the total TH will keep on incrementing. Okay, so this is the demonstration of a timer being in a counter mode. Now earlier we talked about the significance of gate. Now we will now set the gate bit as 1 and see what happens for the timer. Okay, so the bit number 3, okay, is the gate bit. Bit number 0 and 1 are mode. Bit number 2 are bit number 2 is the C/T bar, and bit number 3 is your gate. So I will put it as this is nothing but 09 hexadecimal, or I'll put it as this binary. Okay, so let me now compile this particular program. Okay, and let me open let me put it in the debug mode and open ports as well as the timer, and the timer I will reset all the pins. I will not provide any input to the pin. Okay, and let me run the program. So in order to run the program, I will just run it. So if you see, the timer is not incrementing. Now when the gate is high, at that time the timer will start incrementing if and only if the input provided to the INT0 pin is high. INT0 pin is nothing but pin 3.2. So this is 3.0, 3.1, 3.2. Just observe the value of TH0 and TL0 when I set P3.2. I'm going to set P3.2 now. Okay, if you see, the moment I set P3.2, the timer has started running. If I reset P3.2, the timer stops. I'll do it again. I set P3.2, the timer is running, and reset P3.2, timer stops. So this is called as hardware based timer run. Okay.